introduction to this Chapter 2 from our notebook from the Advanced MRI class that we teach this semester. And I'll begin just going through each of the sections here of this Chapter 2. So we begin by talking about magnetic moments and angular momentum in general. And even though we're going to be talking about the proton and its magnetic moment and the angular momentum are quantum mechanical phenomena, just talking about the classical definitions I think will help build some intuition of what's going on. So we'll begin here. The magnetic moment will define as the current, the product of the current times the cross-sectional area that the current or the loop encloses. And the area has a direction which is perpendicular to the area. That's the vector direction. And the angular momentum has a classical definition which is based upon assuming that you have a particle that has that's rotating at an angular velocity omega, and it has a distribution of mass which is given by the density rho, and the angular momentum is this integral over all space of the density times the distance of that density from the axis squared. And so if the if the mass is distributed uniformly across or throughout the sphere, then you can do this integral, and you can hit this little button if you want to actually see it. And looks like that integral is a little bigger than the screen here. Move that over. There you go. So you can go ahead and do that integral, and you end up with this ratio: 2/5 of the mass times the angular velocity times the radius squared. So we go back, move this back. So it gives us the magnetic moment and the angular momentum. And quantum mechanically, there's a relationship between the magnetic moment and the angular momentum, and there's a gyromagnetic ratio gamma, which is intrinsic to the particle that you're looking at. So a proton has its own gamma, which relates its angular momentum to the magnetic moment. And so if we just consider the case we did above, where we have the magnetic moment, and I believe what we're looking at here is we're assuming, oh, I jumped down a little bit too far, sorry about that, that the magnetic moment is due to the charge uniformly distributed over the surface, which might be the situation if you had a conductor that was rotating, a conductive sphere that was rotating. You have this magnetic moment now that turns out to be omega times the charge times the radius squared divided by 3. And again, if you want to see the derivation of that, you can click that little button and go to the classical definition, which gives the derivation of that. And so the gyromagnetic ratio in this case, which would be the magnetic moment for the spherical surface charge divided by the angular momentum, where the mass is uniformly distributed, ends up giving you 5/6 times q over m. Well, the interesting thing is that the proton has a gamma, which is related to the ratio of the charge to the mass, and it's quite different and from that number. And so we'll talk about that in our lecture, but it relates to how possibly how the things are distributed, or maybe it's just a quantum mechanical phenomenon that is just the way nature is. Okay, well then we're going to spend some time and we're going to talk about magnetic fields. We'll do more of that on the third lecture. But these are the what's called the Maxwell's equations. There's 4 equations that relate the magnetic field and current density in this case, and D is related to the electric field. So the magnetic field and the electric field are related through these equations. And we'll talk about each one as the time permits. But using these, for example, using the fact that the divergence of the magnetic field is 0 and the curl of the magnetic intensity, which is related to the magnetic field, is equal to the current, we can use those 2 relationships and we can derive the function of the magnetic field as a function of the current density as a function of position, and it's related by this integral through all space, and this is called the Biot-Savart law. Using that, we can determine the magnetic field of a dipole, and that will have this relationship, and we'll talk about that, I believe, in lecture 3. And just continuing on, the nice thing is with these relationships, we can predict the motion of a magnetic moment in a magnetic field, and that motion is a type of precession. Let's see if this gives us a little bit more intuition here if I click on that. Probably not. Basically, this is just giving us a derivation of the torque equation, but if we use the torque as a function of which depends on the magnetic moment and the magnetic field, we can get the equation that describes how the magnetic moment changes in time. And we will spend some time on that in our lectures. Okay, moving on. The rotating coordinate system allows us to understand a little bit more clearly what happens as the spin precesses. And finally, we'll talk a little bit about quantum mechanics in lecture 2, because in fact, each proton is a quantum mechanical particle. It turns out if you put it in a magnetic field, it has 2 stationary states, and the probability of being found in those stationary states, they have different energies in the magnetic field, and therefore there's a slightly different probability of being in one state versus the other. And we'll discuss that in lecture 2 and try and make sense of what the distribution is. But it's because of that distribution that we get a magnetization that's related to the magnetic field strength. So it increases as we increase the magnetic field. And then the fundamental constants, the proton's gyromagnetic ratio and Planck's constant. And then inversely related to Boltzmann's constant and the temperature. So the higher the temperature, the lower the magnetization. Lower the temperature, the more you would get magnetized. And that's the fundamental source then of our signal in magnetic resonance imaging. So it's useful to know that. And we'll stop there. We'll get into relaxation later and a few other things. So these are just a short discussion of what we're going to be talking about in the next 2 lectures primarily.